So today we are going to discuss on a very important aspect of the blast furnace, which is about the extending the campaign, or we can say extending the life of blast furnace. And it is really a very important activity, or we can say a very important aspects. So we are not just talking about keeping an old asset running, we are talking about a strategic shift in how we manage the furnace life cycle. So if you look at the uh, bottom of the slide, you will see our three pillars, that is the precision diagnostic, the targeted OPEX, and the asset optimization. So in the past, we would wait for a massive reline, but today we are moving towards surgical data-driven interventions. So the goal here is to keep the heart of the steel plant beating without the massive immediate drain of a full reline. So let me explain what this means in practice. We are looking for ways to defer that massive capital expenditure while actually improving our technical quality. Now, to really understand why this matters, let's look at the actual choice we face when a furnace starts showing its age. So, and this is very important in knowing. So, when we compare the extension versus full reline, so what we are seeing here is a direct comparison of two main paths. Look at the target horizon row. Now a campaign extension buys us an extra 4 to 8 years. So as it shows in the slide, so a full reline is a total reset of 20 plus years, but it comes at a price. A whole system overhaul uh, mm, has a massive downtime, and the core uh, action row where it gets interesting for us as engineers. So in an extension, we are doing targeted step replacement and robotic circuit. So in a reline, we are uh, talking total demolition and reconstruction of the hearth refractory. So look at the note at the bottom. An extension is not a stoppage, it is an engineered strategy deployed when the asset is fully consumed to reduce future capex. But how do we know when it's time to pull the trigger? So that comes to oh, the everything on wear line. So coming to the wear line, which is supposed to be a gaze for us. Now you might think that we just guess when the lining is getting thin, but we have very specific hard limits. Look at this case on the screen. Mark 1. This is the 500 millimeter wear line, as it is showing very clearly in the slide. And when we hit uh, this, we initiate the planning phase. This usually uh, happens about a 3 year before the expected blowdown, because we need that time to engineer solution and procure long lead items. So when we hit Mark 2, as it's shown, our lining went down from 500 to 400 So the 400 wear line is the main anchoring, zero point 0.4 hit mark 2. So this is the red zone. This is our hard limit for safe operation. Once we cross this, we have to prepare for a blowdown. So the decision depends on your local hot metal demand and budget, but the physics of 400 line do not lie. So if we decide on an extension, where exactly are we focusing our efforts? Now coming to the anatomy of the extension, which is totally related with the target invention. So let's look at the anatomy of the extension. This diagram shows our four primary strike zone. So up at the top throat, we are looking at top ring stave replacement as it is shown here. And moving down to the stack and belly, we got the robotic shotcrete and cigar coolers to bridge that wear line. In the cooling system itself, we are doing board stave detection and installing grouting anchor. And finally, down in the lower anatomy, we have a core castable taffel reconstruction. So notice that all of these can be done from the outside or during short outrages. We are not tearing the whole furnace apart. Of course, to hit these targets, we need to see through the shell, which brings us to our modeling tool. Now, coming to the thermographic modeling and float leveler system. So, look at the heat map on the left. This is the thermographic modeling, and it allows us to identify local hotspots, cracks, and residual heart thickness before we ever open the furnace. Then look at the diagram on the right, the float leveler system. This is a simple visual tool for fast detection of board staves. See what red ball. If there is a leak, the water pressure drop and the balls falls. It's a low-tech way to prevent a high-tech catastrophe like water infiltration into the furnace. So in real operation, catching a step leak early is the difference between a minor repair and a total campaign end. Once we find the where we have to fix it, and that's where the robotics comes in. So let us talk about the robotic advantages. So let's talk why we have moved away from the manual labor for lining repair. On the left, you see the old way, manual application. It requires a completely cool furnace, massive scaffolds, and it's dangerous. On the right is our step 1 and step 2. First, we use 360-degree laser profiling to create a digital map of the degradation. And then step 2 is the robotic pod. We lower this pod into the hot furnace and operate it remotely. It uses the laser profile to apply precise, accurately lined shotcrete to the tuyers, Bosch belly and stack. It eliminates the risk of our people and gives us a much better finish. But shotcrete needs something to hang on to, especially in high wear zone. So breezing the wear line with the anchors and coolers. So look at this cross section. We have three key elements here. Number one is the wear line itself, the advancing font of degradation. Number two is the grouting anchor. We install these via drilling for copper strips or welding for cast iron. They reinforce the shell and act as a grip matrix for the incoming shotcrete. And number three is very important, which is towards the bottom right of all these are the cigar coolers. We deploy these to artificially extend the life of copper strip. They basically bridge the cooling gap in those critical area where the original strips have thinned out. So it's like adding a secondary cooling heart to the furnace. So speaking of critical area, let's move to the tap hole, which is often the most important part of the hearth. So now coming to the core castable tap hole reconstruction, uh, this is we can say that this is a strategy that has been proven over 20 years. So step one is the core strategy, a castable design that allow for repair entirely from the outside. As for step two is concerned, it is about execution. We could drill the front portion of the old castable to remove the degraded material and then install new castable and supplementary thermocouples. And step three is the result of low cost, easy maintenance, and most importantly, this only takes a planned 48 to 60-hour shutdown. So compare that to week of downtime for a full hearth rebuild. It's all about a minimal disruptions. Now, if we do have to go for a longer outage, we need a flawless workflow. So the outages workflow, uh, these hexagonal flow represent our standard outage sequence. Let's start with a controlled reduction of burden, the blowdown. Then we move to the salamander tap. Look at the key insight at the bottom. These success of the entire blow-in and the subsequent campaign rest on a high yield salamander tap. We want to leave less than 25% residual mass in that hearth. After that, we quench, then perform robotic hearth cleaning, and finally commissioning. Each step is a critical variable, but draining that liquid iron using internal pressure is the make or break moment. And if that salamander is being stubborn, we have two ways to get it out, and which are very important aspects that we are going to discuss in these slides. Coming to the removal methods, which are consequences of earlier discussion. So coming to the explosive versus oxylan. So how how do we get the solid iron out? We have two main tools. One, the left explosive or dynamite. It's a fast about uh, 32 days for a 1,800 tons removal. It can handle full depth salamander over 3.5-meter thick. The big advantage here is speed and fact that you can walk above the hearth while you are drilling the holes. On the right, the oxylons, it's slower, 37 days for a much smaller 432-ton yield, but it doesn't require a specialized safety footprint of explosive. So if you are over 500 thick, which one would you choose? Generally, dynamite is the winner for the speed. Once the iron is out, we have to cool the heart so we can get in there. So, the quench and hearth cleaning, let us discuss in this slide. So, let's talk about the quench. No quench takes over 6 months. So it's just not practical. Plus, it carries a high risk of CO disintegration for your carbon refractory. Our preferred method is the dry quench. It takes 3 to 5 weeks. We use a complete nitrogen blanket to create an inert atmosphere. The best part is zero water interaction with your hearth refractory. Once it's cool, we move to the hearth cleaning. We use remote execution to remove loose debris and expose the carbon block. Then we do sound trapping with hammers and more core drilling to assess the true integrity of that hearth. Finally, we get to the most dangerous part of the whole process, the restart. So let us talking about a rebirth and risk. So, uh, commissioning, that is about commissioning. So, we are at the finish line, but this is where we see the most mistake. We have cold commissioning, checking every individual system, and the hot commissioning, final test under the live production. So, look at the warning icon. A fast, poorly executed commissioning dramatically increase the risk of a chilled heart that can instantly threaten your newly extended campaign before it even starts. So we often see teams push to recover delays here. Don't let it happen. Quality over speed is the rule for blow in. So let's wrap this up with the core philosophy of this playbook. So coming to the our